show you the invitation to this delightful place. So let me just start by a brief history of QBism. I think the first paper that sort of one should count is this one here, with Carl Caves, Chris Fuchs, and myself, where we introduced the idea of interpreting quantum probabilities as Bayesian subjectivist probabilities. So QBism, as a full interpretation of quantum mechanics, I think really saw its light in 2010, this paper by Chris Fuchs, QBism, the perimeter of quantum Bayesianism. And QBism became, let's say, famous, well-known, with David Mermin's paper in Nature. So QBism is related and has similarities to Copenhagen, but it's not Copenhagen. In some sense, it fixes problems with the Copenhagen interpretation. So in QBism, probabilities are an agent's personal degrees of belief. This includes probabilities 0 and 1, and probabilities derived from pure quantum states. So all probabilities. Quantum states, just as probabilities, represent an agent's personal degrees of belief. And measurement outcomes are personal to the agent who performs the measurement. So that's in a nutshell so the key tenets of QBism. Let me just say something briefly about the B in QBism. So people usually assume it's Bayesian. But Bayesian is too specific and too narrow. In particular, it suggests it suggests a particular updating rule, Bayes rule, as the center, which is really not that much stressed in this approach. But secondly, also, many Bayesians in statistics, they are objective Bayesians. A big part of Bayesian theory is the attempt to find an objective prior, so that all practitioners can agree on the starting point. Now, we de-emphasize this. We don't want that. So no, not Bayesian. How about B for Bruno de Finetti, quantum Bruno de Finettiism? I mean, that's not going to catch on, but it's actually closer to what we want to say, because the kind of probability theory, the interpretation of probability we have in mind is actually very close to de Finetti's interpretation, as was explained this morning already. So Bruno de Finetti is better. Even better is betabilitarian. Betabilitarianism is actually a real term. It was introduced by Oliver Wendell Holmes, who was a United States Supreme Court judge, I think in the early 1900s, and a pragmatist philosopher. And for him, this was the idea that the world is bettable. So we can actually navigate the world by placing bets and by making good predictions, really. So that's pretty good. But of course, not going to catch on, because quantum betabilitarianism, that doesn't work. So what we promote at the moment is just B. This is something that I should do an experiment. I've got a fair coin here, just an ordinary euro coin, and let me toss it a few times. Heads. 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 I could carry on. So the point I want to make is that, it's a fair coin, probability 1/2, 1/2, you would think, but that's probability assignment. 1/2, 1/2 is not a property of the coin. Right? Because it also depends on how I toss it. And there are people who actually can do this, who can make it land heads up every time. I can't. But so it's not a property of the coin. You might think then it's a property of coin and tossing mechanism. But in a classical world, that doesn't work either, because if I really specify how I toss the coin, it will land the same way each time. So it's also not that. The point that has been made before in this conference is, well, probability assignments start from a prior probability. The idea that this coin is has a 1/2 probability, depends on initial conditions and maybe some uncertainty in there and my inability to control things properly. So it starts from some prior probability. So in classical mechanics, the idea of having personalist, non-objective Bayesian probabilities is very natural. But of course, the whole problem is quantum mechanics, and this is what this talks about. So personalist probability started from De Finetti and Ramsey in the 1920s, 1930s, and I think was really put on a very firm and good footing in 1954 by Savage in his book, The Foundations of Statistics. Savage's book was enormously influential in the social sciences, especially economics, but certainly not so much in physics. So in that theory, the rules of probability theory are grounded in decision theory. It's a question of how should I act. They have a normative character, how should I act? And they can be derived from the requirement of no sure loss. In the simplest case, Dutch book coherence. So I'm going to just present to you in a second a very simple Dutch book argument. But that is, I mean, this is a very simplified version of the whole story. Savage gave a fully fledged axiomatic derivation of decision theory, and he didn't derive just probability as a calculus, but also utility theory. So the idea that a decision is determined on, the idea of maximizing expected utility comes out of that. So in this simple-minded version I'm going to present, well, a probability, my probability of an event E has to do with what bets, what gambles I am willing to take. So it is P, my probability of E is P, if I regard P dollars as the fair price of a lottery ticket that pays $1 if E occurs. And so, of course, the price should be between 0 and 1. $0 and $1. So that's sort of this idea of a action-based definition of probability. These probabilities always inform action. Accept the gamble or don't accept the gamble. And of course, you can easily take this to any situation. Experimental physics, for instance. I mean, obviously, it's always making decisions on what you will expect. And if you're in engineering, you want some result to occur and so on. Okay, so here's my Dutch book argument. So it's a three-way horse race. Not very realistic, but there are only 3 horses in this race, and these are the odds offered. So even odds on horse 1, 1 to 2 on horse 2, and 1 to 3 on horse 3. And I'm a sophisticated gambler, so I place a combined bet on these 3 horses. So I bet a total of $260, should be euros. So $120 on horse 1, 80 on horse 2, and 60 on horse 3. And so I think, well, I mean, I hedge my bets, and so I have some reasons to believe that this is good. And now, but if I do a little bit of analysis, I found the following. Let's see. Let's look at the 3 cases, right? Horse 1, 2, or 3 can win. So if horse 1 wins, well, the payout is $240, right? But I had gambled 260, so I have a net loss of 20. That's not good. But surely horse 2 will do better, but it doesn't, because again, if horse 2 wins at these odds, well, I get $240 and I have a net loss of 20, and you will guess what happens for horse 3. Again, you lose $20, right? So what's going on? Well, I mean, most people are not that used to look at odds, so that's why this is a nice example. But if you look at the implied probabilities, okay, no, first let me make this point, sorry. Should follow the reasoning on my slides. So this is remarkable and unusual, especially for physicists, because in physics, usually what we think of is the long run. So the rules of roulette, the probabilities, they work because in the long run, you are guaranteed to lose. In this case, you're certain to lose in this single instance. There's just one horse race, and you're guaranteed to lose in this one horse race. and so the reason is easy to see. The implied probabilities here are 1/2, 1/3, and 1/4. They correspond to these odds. And if you add them up, you have 13/12. So by gambling according to these odds here, you violate the rules of probability theory. You violate the Kolmogorov axioms. And now there is a remarkable theorem, it's a very easy theorem actually, that whenever you violate in your betting decisions, your betting odds, whenever you violate the rules of probability theory, this kind of situation can be constructed. This situation is called a Dutch book. So you're being Dutch booked here. So here's the definition. An agent's betting odds are called Dutch book coherent if they rule out the possibility of a Dutch book. And then the simple theorem says an agent's betting odds are Dutch book coherent if and only if they conform to standard probability rules. And so this is this decision-theoretic derivation of the probability rules. And so Dutch book derivation gives you normative theory. How should I gamble? So let me say a little bit about frequencies and repeated trials. So one objection, I mean, I'm talking about physics all the time because I used to be a physicist. And that's, of course, always an objection. But physics is really about doing experiments. And probabilities are clearly, I mean, they in the long run, they always become equal to the observed frequencies. So and this is just basically mixing up concepts. Frequencies are data. So in probability theory, frequencies are, well, they are, what are they called? Events. Whereas probabilities, they are probability measures, they are probabilities. So they're just different things. In this Bayesian framework, frequencies are data, probabilities are degrees of belief, and they're just different categories. But of course, frequencies can be assigned probabilities. You can have a law of large numbers. The probability that your frequency lies between these narrow values is almost 1. There's no mixing of the concepts there. And of course, the other way around as well. Frequencies inform probability assignments, and of course, often our most powerful way of finding probabilities. You have lots of observed data, and of course, you can assign good probabilities. So they're just different things. And one reason that this subjectivist, personalist approach is powerful is that it makes this distinction very clearly. So it doesn't mix up the concepts, you don't get in a muddle. The De Finetti's theorem was mentioned, and I would also like to mention it, basically as sort of self-advertisement here. One of the best mathematical results that this QBist quantum Bayesian approach has brought about is a quantum De Finetti theorem, actually, at least a very simple proof of the quantum De Finetti theorem. So this is just the quantum mechanical versions of the classical De Finetti exchange, the representation theorem. Well, it works like this. If you have n trials, n physical systems, and they have this exchangeability property, so that there is symmetry under exchange of systems, and also these n systems, these n trials, are actually part of a sequence, of an infinite sequence with that exchangeability property. Then the quantum state of these n systems can be written like that. And that is simply saying that, well, in words, it just says that the total quantum state can be thought of as every of your n subsystems being in the same state rho, and you just don't know, there is some ignorance about what state rho that is, and you integrate, and this gives you your total quantum state. And one thing this achieves in a very nice way is defined what you might mean in physics by a repeatable trial, or by a repeated trial. Because my physics is very much based on the idea that you can repeat experiments, and you get lots of data by repeating experiments many times. And this gives you a mathematical definition of what that means. So you have a repeated trial if the total quantum state of your many repetitions obeys this exchangeability criterion. And I should only mention, but exchangeability is not something you can derive by looking at your end systems. It's an assumption. It's a belief. It's a degree of belief itself. But this is a very powerful theorem because it connects this subjectivist theory with the ordinary frequentist statistical analysis that is often done in physics. One more example. I've used the word normative several times. And I just would briefly give an example that tells you what I mean by normative and what's the distinction between a normative versus a descriptive view of probability. And this is a very famous example by Allais from the 50s, which actually gave rise to a lot of progress in economic theory. Kahneman got the 2002 Nobel Prize, which is based on ideas that started there. It was mainly the observation that economic agents are not rational. Because before Kahneman, economists had to try to model decision makers as rational agents, and they are not. And this will probably convince many of you, some of you hopefully, that you are not rational either in your intuition, so you need the theory to keep you honest. So here's a choice I give you. I offer you $5 million with certainty. That's one choice. I'm not really doing that. The second choice is you get nothing with probability 1%, 5 million with probability 89%, and 10 million with probability 10%. Which do you choose? I mean, I'm pretty clear what I would choose. I would choose 1A. Because, well, I mean, I couldn't stand the regret if that 1% happened. Here's another choice, 2A or 2B. So same payoffs, but now for 2A, you have 89% with, you get nothing with probably 89%, or 5 million with probably 11%. That's 2A. And in 2B, you get nothing with probably 90%, and 10 million with probably 10%. Now, my intuition is to choose 2B because really, I mean, who can distinguish between these numbers, right? And if you do that, I mean, basically, you're just plain inconsistent. So that's just because they're just the same thing. Only on the right-hand side, you just mix in something that is just these 89% zero. You just mix them in, and so it's just the same thing. So you shouldn't. So that's an example for where real agents are actually in the intuitions inconsistent, and they need probability theory as a normative rule. Okay, so this is the distinction here. Okay, so now, so let me say something about probabilities in QBism here. So they're not objective, but represent an agent's personal judgments, just like in personalist theory. They're not epistemic. They're not about knowledge. So it's not like they're not like probabilities in Bornstein mechanics, where the probabilities you write down are probabilities about the unknown real position of your Bornstein trajectory, for instance. They're not epistemic, but they inform action. And the rules are not descriptive, so they're not psychology. They don't describe how physicists actually make decisions or what states or what things they write down. They're normative. They tell you how you should act, and therefore give you guidance on how you should build machines, etc. And so these two slides are almost identical. This is about quantum states, and this is just the same thing. Quantum states have exactly the same status here. They represent an agent's personal judgments. They inform action. And the quantum formalism, in particular the Born rule, because I mean there is a branch of, not a branch, an effort, a big effort in QBism to derive the quantum formalism from simple sort of QBist principles, where the Born rule emerges as really the sort of the the centerpiece. So the quantum formalism, in particular the Born rule, is not descriptive but normative. So in that sense, so QBism, so the Born rule, or the quantum formalism in general, just the Hilbert space formalism of quantum mechanics, it is like probability theory in that it connects degrees of belief. It's like probability theory, which is an objective theory. The Born rule and the quantum formalism is objective. It's not something that any individual basically can choose. It's based, unlike probability theory, it's based in experiment. It's empirical. It's something we found out about the world. Whereas the probability calculus, as I just described it, is actually something that just comes basically out of simple axioms. Actually, one axiom: don't hand over money, and that gives you the probability calculus. So this is empirical. So this is actually very unlike probability theory in this sense. And so QBism, in this sense, has similarities with structural realism, where the actually objects, the quantum states, etc., even measurement results, they are not objective out there real, but the formalism, the structures, they are. Here's something that David Mermin described as the thing that physicists might find most difficult to swallow, and it took him a long time to swallow that. This is about probability 1. So you may remember that I said that probabilities are subjective judgment, personalist judgments, even if equal to 0 and 1, and even if derived from pure quantum states. And you just need this to make the quantum interpretation consistent. Otherwise, you run into all these paradoxes, measurement paradoxes, etc. So, and here's an example for why this actually makes sense, and also I'm telling you what consequences it has. So here's another horse race. Let's say there is a horse called Albatross. This is an actual horse name. I looked this up on the internet. I'm certain that Albatross will win. So my probability is then for A wins is equal to 1. So that's, according to what I just explained, means I'm willing to pay any price less than $100 for a ticket that pays $100 if Albatross wins. That was the definition. But what it doesn't mean is that there's no objective feature of the world that guarantees that Albatross wins. They're just two different things. And of course, one very easily, very often intuitively conflates these two things. If probability is 1, well, it can only be 1 if there is something in the world that makes it happen. And actually, this is actually a crucial piece of the thing, because it leads to a rejection of the Einstein-Podolsky and Rosen criterion of reality. It's a very famous sentence from the EPR paper, 1935. If, without in any way disturbing a system, we can predict with certainty, that is, with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. And this, of course, is in direct contradiction to this QBist principle that even probability 1 judgments are judgments. And it's crucial if you want to interpret and understand Einstein-Podolsky, Rosen correlations, Bell inequalities, etc. QBism, so I basically now told you how we use, I told you a little bit of how it makes sense to use personalist probability in physics, its connection to frequencies, etc. But I didn't really tell you what I also told you how you can interpret the quantum formalism and the Born rule in this way, even without giving you much detail. But I started out by saying, well, that it might be counterintuitive to use this subjectivist or personalist approach in quantum mechanics, because some of probabilities seem to be really deeply embedded in the theory. And what I believe, on the contrary, is that quantum mechanics gives you, especially quantum information theory and quantum interpretations, gives you far stronger reasons to use subjectivist probabilities than classical mechanics. And a very brief overview of things that QBism achieves, it resolves paradoxes. It basically leaves no quantum paradoxes. And it removes mysteries. Collapse of the wave function is one. I mean, if the wave function is something that captures my belief, if a measurement happens, well, all I'm doing is updating my beliefs. There's no mystery about collapse at all. There's the measurement problem. Wigner's friend, which just recently became very, very popular in the media, QBism has no problem whatsoever with that. You're going to hear about Wigner's friend tomorrow. It's Czaslaw here. Czaslaw is going to talk about, Czaslaw Bruckner is going to talk about Wigner's friend tomorrow. Oh, there he is. And there's non-locality. I'm going to say a little bit about that. There's no cloning, the no cloning theorem. There's the mystery that's removed. There's quantum teleportation. And let me just do another experiment, my quantum teleportation experiment. Not quantum. I mean, here's quantum teleportation. This is what it does. Alice in Vienna and Bob in London, they share a perfectly entangled pair of qubits. Each has one, and they have these perfect quantum correlations. And you're also in Vienna. You have in your possession a qubit in a state psi. And that just represents your belief about the qubit. Okay? Now, you hand your qubit to Alice, and Alice and Bob go through some motions that do not involve them ever finding out what psi is. They just make a joint measurement. Alice makes a joint measurement on the two qubits, and she sends 2 bits of classical information to Bob, and Bob then performs some operation on his qubit. And the result is that now psi represents your belief about Bob's qubit in London. That's what's happening. So there's no mysterious sort of teleportation of any substance going from here to there at all. All that happens is that your belief about this qubit now suddenly becomes your belief about that qubit. That's all. And that can be done. I will do now a teleportation experiment with coin, because I believe that's illuminating. So let's see. So basically, I need 2 perfectly correlated coins. I can just flip them the same number of times, which means that I know they're perfectly correlated, but I don't know whether they're heads or tails. Okay? This is London. This is Vienna. And now here's another one. And this is yours. So you basically, let's take a 50-cent coin for that to distinguish it. So basically, I can show you this is heads, and then I flip it this many times, and now you form a belief about what it is. It doesn't matter what your belief is. You have a probability of heads equal to Q. Each of you might have a different Q, right? And so what I now want to do, you hand me the coin. You've done this now. I've got the coin. I'm Alice. And now I go through the motions. What are the motions? The first one is I make a parity measurement here. So without learning what this qubit is, I just try to find out whether they're the same or not. I can actually really do this in practice because I just need to flip them the same number of times. Even by now, I've forgotten whether it's even or odd the number of times I flipped it. So I now know that odd parity, they're different, without knowing what this one was. Actually, that state is destroyed now, right? So, but I have the odd parity, and now it comes. Now I send 1 bit over there, so that's just 1 bit classically. And the rule is that if the parity is odd, I flip this one over without looking at it. And now you believe originally about that coin, which was destroyed. In the meantime, now suddenly is your belief about that coin over there. That's how teleportation works. And the QBist claim is that there is nothing more mysterious at all in quantum teleportation than that. That's all. Well, that's the way in which QBism removes mysteries and clarifies things. There's a long, long list, actually, of phenomena in quantum information theory, which can be almost trivially understood if you take this viewpoint. No cloning is another one, for instance, which always is described as some deep mystery about the quantum world. Okay, so here's, I need to not forget my money. So locality. See my final thing here. That's the idea that an object is directly influenced only by its immediate surroundings. Okay. And that was key for Einstein. He didn't see how physical laws could be formulated and tested without it. Well, if you look at the media, not so popular, especially in the last few years after the loophole-free Bell inequality tests, well, there are claims everywhere that nature is non-local. For instance, here, I mean, nature published this article here that claims that these experiments plugged loopholes in previous demonstrations of action at a distance. I mean, claims non-locality. Here is a philosopher of science, influential philosopher of science. He says what Bell proven of theoretical physics has not yet properly absorbed is that the physical world itself is non-local. So I would like to stand against that. There is no evidence for that from the experiments. And Einstein essentially knew that. I mean, so here's a letter from Einstein to Schrödinger, 1935, same year, but not the EPR paper, and actually quite a different message. And he's looking at a non-local situation, Alice and Bob, A and B, he calls them. And his argument, and in quantum mechanics, you probably know, if you have entangled particles, A and B, then the kind of measurement I perform here actually influences the state of the particle over there. So there's no doubt about that. That's called steering. It's well understood. It's just a consequence of the formalism. So Einstein understood that. He knew that. And so his argument is this. But now the real state of AB, the two particles, let's say, consists precisely of the real set of A and the real set of B, which two states have nothing to do with one another. The real set of B cannot depend upon the kind of measurement I carry out on A. So that's locality for Einstein. Then he actually comes up with a puzzling conclusion. He said that we need to give up the position that the psi function constitutes a complete description of a real factual situation. There is a very nice article about these arguments by Harrigan and Speckens a few years ago, and they conclude that he just messed up here, because the real conclusion he should have taken is this one here. It just shows that psi, the wave function over there, is not a function of the real state at B. Because by doing the measurement here, you cannot change the real state at B, but you can change the wave function. So therefore, the wave function is not a real property of the system at B. That's the conclusion from this argument here. Now, Einstein hoped that he can change the quantum formalism. The loophole-free Bell experiments have dashed that hope. So therefore, the conclusion, one possible conclusion is, if you accept locality, well, that psi is not a real property of the system, which is the QBist conclusion. But you do not have to abandon locality if you don't want to. You can become a QBist instead. Now I will finish with another Einstein quote, again about probability. I still do, this is a letter to Fritz Reiche and his wife, August 1942. I still do not believe that the Lord God placed dice. If he had wanted to do this, then he would have done it quite thoroughly and not stopped with a plan for his gambling. In for a penny, in for a pound. That's wenn schon, denn schon in the German original. Then we wouldn't have to search for laws at all. Okay. The usual reading, of course, Einstein addressed deterministic laws. The QBist reading, well, there are indeed no laws. The laws are not descriptive, they are normative. God has done it thoroughly. There are no laws that determine objective probabilities for measurement outcomes. The world does not evolve according to a mechanism. What God has provided is tools for agents to navigate the world, to survive in the world. Thank you.